In today's lesson on thermochemistry, I'm going to discuss two different strategies that chemists use to calculate the enthalpy change of a reaction. The first is to use tabulated molar enthalpies of formation. This is a really straightforward and quick approach to calculating an enthalpy change of a reaction. The second is to use the bond enthalpies, which is a really good way for us to review Lewis structures, but also to calculate things that we may not have molar enthalpies of formation to use. I'm then going to discuss a property of matter known as the specific heat, which is the energy that's required to change 1 gram or 1 mole of that substance 1 degree Celsius or Kelvin, and the strategies that chemists employ to measure this specific heat, which is known as calorimetry. I'm going to then discuss heating curves, which is the energy changes that occur when you heat a substance that may or may not involve a phase change. Lastly, I'm going to touch on the molecular basis of heat capacities, which involves the translational, rotational, and vibrational modes of a molecule, and how those can store energy. And this naturally leads to a discussion on spectroscopy, which I'm not going to get to today. But nonetheless, it's a really interesting topic, and I hope you enjoy that part of the lesson. And this is the last lesson of General Chemistry 111, so thank you for watching my videos. If you have any feedback, I'd love to hear them. Let's go ahead and get started. So on the last lesson, I discussed molar enthalpies of formation for a compound, and I think it was nitrous acid. And what that was the heat that's required or given off in the formation of 1 mole of a substance from its standard elements. And we're going to start by looking at the formation of acetylene, which is the compound C2H2. And this compound can be formed from carbon and hydrogen, and it gives us and it requires 227.4 kilojoules of energy per mole. Now remember, a positive value here means this is an endothermic reaction, meaning it requires an input of this much energy to occur. Now, acetylene probably can't be formed by passing hydrogen over carbon. This is more of a theoretical formation reaction. But nonetheless, this would be the energy that would be required if this were to occur. Now, how do I know that carbon and hydrogen are the standard elements of these two elements? Well, there are a couple ways that we can figure this out. My strategy is to just look at a standard thermodynamic reference table, and this is posted in the module. And if we look, we'll find 4 different columns here: the substance, the change in the enthalpy of formation, the entropy, which is given by the symbol S, and the change in the Gibbs free energy, which is given by the symbol G. We're going to be learning about entropy and Gibbs free energy in Chem 112. But for Chem 111, we can look at the delta H values here. And for every element, there will be some value that will be 0. And that tells us that this aluminum in the solid form is the standard state at 25 degrees Celsius and 1 bar of pressure. So if we look for carbon, we'll see that carbon actually exists in 2 solid forms, graphite and diamond. And graphite is the more stable state of carbon, so it's going to have a delta H value of 0. And for hydrogen, we see that hydrogen normally exists as the diatomic molecule, not as the free hydrogen form. And so we're going to want to use the H2 value. So let's go and look at a different reaction. If I want to form magnesium carbonate, that would have to be formed from the standard elements of magnesium, carbon, solid, which is the graphite form, and oxygen. For this molecule C5H11NO2, this could be formed from 5 carbons, 11 halves hydrogen, 1/2 nitrogen, and 1 oxygen molecule. So you'll notice that I'm making use of fractions in these formulas, and that's because in order to form 1 mole of these compounds, I need to use fractions here. And this is the requirement actually for these. Okay, so to actually carry out some of these reactions may be usually impossible. So if I want to calculate some of these reactions, I can use Hess's law to do this. And say, for example, I don't know what this value is. So if I'm trying to solve for the heat of formation of acetylene, I don't have the value 227.4. How would I do that? Well, we could start by combusting acetylene gas, which is the reaction with oxygen to form carbon dioxide and water. And for combustion reactions, I'm going to be using water in the liquid state, or water vapor. And we can look up this value in a different table, or we could carry out the measurement, carry out the reaction and actually measure this, but that's a little bit of work. So this other table I have here lists acetylene with a delta H combustion of 1,300 kilojoules per mole. And we'll notice that all these values are positive, even though combustion reactions are highly exothermic. And if we read through the details here, it says that it's just defined as the negative of the enthalpy change of the reaction. So the actual enthalpy change is negative. So that's where I'm going to get this value of negative 1,300 kilojoules. Well, if I have this reaction, I can manipulate it to solve for the delta H of formation of C2H2 using Hess's law, which is a strategy that we learned in the last lesson. So what we'll need is we'll need some reaction that forms carbon dioxide and some reaction that forms water vapor. Now, the simplest reaction that forms carbon dioxide and water vapor is carbon plus oxygen and hydrogen plus 1/2 oxygen. These values can be found in the reference table here. So carbon dioxide is right here, negative 393.5, and water vapor is negative 286. You want to make sure we're grabbing that value and not the gas one, because we'll get a value that's slightly different. All right, so what we're going to do first off is use Hess's law to calculate out what the delta H of formation of C2H2 is. So what we really want to do is we want to add those reactions together to get this reaction. So let me rewrite that out. Not O2, H2. So we're going to try to combine these three to give us this overall reaction. And we'll notice that acetylene is given in the first reaction, but it's on the wrong side. So what we can do is we can flip this reaction. And when we flip it, we're going to have to change the enthalpy to be positive. The next thing that we might notice is that we have carbon on the left side. But this reaction here lists carbon with just 1 mole. So we'll need to multiply this reaction by 2 and this enthalpy of formation by 2. Lastly, we'll see that hydrogen is exactly where it needs to be, and we're not going to have to make any changes there. And then about the oxygen, right? So the oxygen is in these other 2 reactions. So hopefully when we add them together, the oxygens will cancel out, and they will. So let's see what happens here. I'm going to start off by rewriting all these reactions. So I'm going to flip the first one. And and then we'll multiply the second one. And then for the last one, hydrogen and oxygen, we're going to keep that one the same. All right. So when I go to add these three reactions together, we'll want to cancel everything that's the same on both sides. So first off, I have two carbon dioxides on both sides. I have water on both sides. And then for the oxygens, on the left side I have 5/2, and then on the right side I have 5/2, so those cancel as well. And then we end up getting this overall reaction that we were targeting. So all we need to do at this point is add these enthalpies of formation together, and what we'll get is exactly what we were hoping for. 5.8. So that comes out to be 227.2. And this is a formation reaction because we're forming acetylene from its elements. And these are all at standard conditions, which are 25 degrees Celsius in 1 bar. So 227.2 kilojoules. And if you remember from above, that is pretty much the same value that we have up here that we grabbed from the table. Now, this is kind of an interesting thing because if we look at this in a little bit more detail, we'll see that we added together a combustion reaction. So we took this combustion reaction, we had its delta H value, and then using the heats of formation of two of the different compounds, the CO2 and the water, we were able to figure out the heat of formation of a different value. And the oxygen is already in its standard state, so we didn't need its heat of formation. So essentially what we did here is we summed together the heats of formation of the products of this combustion reaction, and we subtracted the heat of formation of the reactants, or we could say that we added the negative of it. But really what we're doing here is we're making use of this shortcut. The heat of any reaction is just going to be equal to the heat of formation of the products minus the heat of formation of the reactants. So let's look at this one more time and see how we can make use of this this formula. So I'll rewrite the combustion reaction. So C2H2 plus oxygen gives us CO2 and water vapor. And then we have 4. Was this 5/2? All right, so we can take this so overall this delta H value is equal to the combustion reaction of negative 1300. And if we want to figure out what the delta H values of this thing is, we don't know what it is, we can make use of the other heats of formation. So for oxygen, this one is already in its standard element, so it's 0. For CO2, this is going to be negative 393.5. Now there's two of them, so we'll need to multiply that by 2. And then this one is negative 285.8. All right, so conversely, we could, if we knew all 4 of these, we could calculate the delta H of the combustion. Okay, so let me show you just that this works out. So we'll set this equal to delta H of the reaction. And then we'll sum the products, which are these ones over here on the right. And usually what I'll do is I'll write it like this. Okay, so what we're going to want to do then is just kind of replace these values. We'll see that this one and this are the same. These are the same. This is this value. And these are all kilojoules per mole. I just leave out the mole portion here. So 2 times CO2, there's 2 moles of it. I'll usually like using a question mark here. Question mark plus 5/2 times 0. So this just comes out to be 0, right? So 0 times anything is 0. So now I can evaluate what's here in these brackets. Okay, so that gives me negative 1,000. Hey, Hemingway. Okay, sweet. So now all I need to do is I'll move the heat of formation to the other side. And move the 1300 to the other side. And what do we get? We get the same value, 227.2. And I think this method is a lot more straightforward. So let's go and practice this with a couple other problems, and let me show you that. We can write it as kilojoules per mole or kilojoules, because the heat of formation is always per 1 mole of that substance. Cool. So that's how you can make use of Hess's law, and specifically using the molar enthalpy of formation shortcut. Okay, so this is a link to that reference table I was using. The other reference tables are available on the module. So let's make use of those values to figure out the heat of formation of each of these different substances. So first off, this is 2 moles of HF being formed from H2 and F2. All right, so hydrogen and fluorine gas, those are the standard states of those 2 substances. HF, this is actually essentially a heat of formation. This is the 2 times the molar enthalpy of formation of this substance. So if I go and try to calculate this one, we're going to find in the table really quickly that hydrogen has a delta H of 0, that fluorine has a delta H of 0, and HF has a different value. It's negative 271. Okay, so that is the value we're going to need, negative 271. So the delta H of this reaction is going to be equal to 2 times, I already forgot what it was, negative 271 kilojoules per mole. That's our products minus our reactants. There is, both of them are 0 because they're in their standard states. So here we're essentially just finding twice the enthalpy of formation of HF. That one we really don't need to make use of this equation because it should be pretty obvious from looking that over. Okay, so this would be just negative 542. All right. The next one is hydrogen and nitrogen to form ammonia. Again, we have these right here. These are already the standard states. So this is this is essentially twice the heat of formation of ammonia. So both of these equal 0. So this is 2 times the heat of formation of ammonia. And so we can just look that value up in the table. Ammonia would be under nitrogen, NH3 gas, negative 46. So 2 times negative 46. And that gives us negative 92 kilojoules per mole. If you remember this reaction from earlier in the semester, this is the formation of ammonia in the Haber process. So this reaction now we can determine is exothermic, and it releases negative 92 kilojoules for every mole of ammonia that is formed. And specifically, for every 2 moles of ammonia that are formed, it's negative 92, actually. For every 1 mole of ammonia that's formed, it's negative 46. So that's quite a bit of energy that's released during this process. So it's kind of interesting that this reaction requires a lot of energy to occur, because you would think it would be releasing energy. Well, this reaction, despite what it might look like from an enthalpy standpoint, we're not looking at the Gibbs free energy or the entropy changes that are occurring here. So this is just the heat component, and you'll learn about more of those other processes in Chem 112. So there's more thermochemistry to learn here. Okay, so these other 2 problems, we have carbon monoxide formed with oxygen to form carbon dioxide, and nitrogen oxide with plus oxygen giving us nitrogen dioxide. And both of these aren't just heats of formation reactions. So we have to make use of the heat of formations of these other things. So CO, let's find that value first. Okay. So negative 110.5. I think what I need to do is download this. That's better. I want to grab these other ones while I'm here. Nitrogen oxide is 90. This is 0. And then NO2 is 34. So what we can do is we can find, since we know all the heats of formation, we can find the enthalpy change of this specific reaction as it's written. We'll take the product's enthalpies of formation times the number of moles. And we'll subtract the enthalpies of formation of the reactants times their moles. All right, so this first one here. And it's best to use parentheses here. It's really common to get a sign error when you're doing this. And the other part's just 0, so negative 566. And then the other one, not formation. So you can see that this is a fairly quick way of calculating these, and doesn't require all that much effort. Just kind of understanding the basics of like how this works does take a lot of effort. I feel like it is one of the topics that is harder for me to teach for sure. Okay, so overall, these two reactions on the bottom are also exothermic. So they release a lot of energy when they form. That means that these products here are more stable than these reactants by themselves. But it still might be difficult for these reactions to occur. So that's, again, kind of something you'll learn more about in Chem 112. All right, so now the next approach to calculating the enthalpy of a reaction is to make use of the bond enthalpies. And this is something that we're kind of familiar with already from all the atomic structure that we've learned and molecular structure that we've learned. We know that there is some potential energy that's stored in the bond between two atoms. And if we want to break apart a molecule, we're going to have to input energy to break the energy that's of attraction that's stored in that bond. And if we form a new bond between two atoms and form a new molecule, actually we're going to end up having energy that's released in that process, because now those products are more stable, so that excess energy gets released as heat. So we can see that if we have the formation of water from hydrogen gas, 2 moles, and 1 mole of oxygen gas, we need to break the bonds between the oxygen, which is a double bond, and then we need to break the bonds between the hydrogens here. When we do that, we form hydrogen and oxygen in the gaseous state, and then we recombine all of those atoms to give us our water molecules that have single bonds between the hydrogens and the oxygens. So what we're looking at here is the breaking of 2 hydrogen single bonds, 1 oxygen double bond, and the formation of 4 oxygen-hydrogen single bonds. And we can average the bond enthalpy for each of these to help us calculate this process. Now, the delta H of a reaction can be estimated by simply adding the energy that's required to break all the bonds in the reactant molecules and subtract it from the energy that's evolved as heat upon the formation of all the bonds in the product molecules. So what this looks like is that the delta H of the reaction is approximated by the enthalpy of the bond of the reactants minus the enthalpy of the bond of the products. And this is kind of curious because from what we were just looking at above, we were taking the enthalpy of formation of the products minus the reactants. But here we're doing the opposite. We're taking the enthalpy of the reactants minus the products. The reason why this is the case is because bond enthalpies are typically tabulated as positive values. Although a bond enthalpy would kind of make more sense to be tabulated as negative, we do them all as positive. So that's why it's reactants minus products. So just remember that, and the more practice you get with this, you'll get it, no problem. So this is a table from your textbook, and it gives some of the molar bond enthalpies for the different bonds. We already kind of expect that triple bonds are going to require more energy than single bonds. And then for elements that are like larger, like bromine, they're going to have less energy than a chlorine bond. But kind of interestingly, a fluorine-fluorine bond is not as much as I would have thought. So some of these are difficult to predict. And one thing to keep in mind is that all these values in this table are average values. So the nitrogen-hydrogen bond energy isn't always going to be 390 kilojoules per mole. It depends on what molecule it's a part of. So that's why these are going to give us approximations to enthalpy of a reaction. They're not as reliable as measuring it. And we can compare a couple of them that we calculate to what we would get from heats of formation. And we can find that they're generally within 10-15%. So they're a good approximation. So here's our first example. I have chlorine trifluoride being broken into chlorine and 3 fluorine atoms. And I measure that this enthalpy change is a positive 523 kilojoules per mole. Well, from this information, I can calculate the bond enthalpy of a chlorine-fluorine bond, specifically in a chlorine trifluoride molecule, by realizing that there are 3 chlorine-fluorine bonds, and that for each of them, the average energy would be 523 divided by 3. So if we draw out this molecule, good review here of Lewis structures. There's a total of 7 times 4 or 28 valence electrons, and 7. Wait, what is it? Yeah, 28. And so far, I've distributed 24 of them. So this molecule is T-shaped. It's got a 2 lone pairs here on the chlorine. Now, those lone pairs aren't going to be important here. What we're going to be looking at is that there's 3 ClF bonds here. So if I want to break that, 3 times the enthalpy, the bond enthalpy of a ClF bond should be equal to the change in enthalpy of the reaction. Because there's no bonds here that are formed. They're only the bonds that are broken. So to calculate the bond enthalpy here, we just need to divide the change in the reaction by 3. it's easy for me to see this. Sometimes that's a little bit harder for me to explain. But that's, I think, how I would write it mathematically. So 523 divided by 3 is 174. And what I'm going to do is I'm going to leave these all as equal signs, but they're really, again, somewhat of um, well, this would be what the bond energy is for this specific molecule, but a ClF bond may vary, right? So keep in mind that these are kind of approximations. Okay, how about this next problem where I want to estimate the change in enthalpy for the formation of carbon tetrafluoride and chlorine from carbon tetrachloride and fluorine. So this is going to require the breaking of a lot of bonds and the formation of a lot of bonds. So let's draw out these molecules. So that's our first molecule, then fluorine. And then on the right side, these all have lone pairs here. Okay, and then chlorine. Sometimes a lone pair is just kind of getting in the way. Okay, so there we go. And what we're doing here is we are breaking 4 carbon-chlorine bonds and a fluorine-fluorine bond, and we're forming these 4 new bonds and this new 1 bond. Okay, so what we'll do here is we'll estimate the enthalpy of this reaction by taking the enthalpy of the bonds of the reactants and subtract it from the enthalpy of the bonds of the products, which are the bonds that form, and the ones on the left are the bonds that are broken. Okay, so we have 4 times the bond enthalpy of carbon chlorine and 1 times the bond enthalpy of fluorine fluorine. And then on the right side, we'll have 4 times the bond enthalpy of carbon fluoride, CF, plus 1 times the bond enthalpy of chlorine, chlorine. Okay. So carbon and chlorine is 331 from this table here. And then fluorine and fluorine is 155. And then carbon fluorine is 439. And then chlorine chlorine is 243. So this reaction should evolve 520 kilojoules per mole. And we estimated that through the bond enthalpies. All right, that's pretty much how you do those types of problems. And you can also estimate the bond enthalpy as well if you know the enthalpy of the reaction. So you can estimate bond enthalpies as well this way. I think I'm going to do that in this next problem. So let's calculate the average bond enthalpy of a carbon-hydrogen bond in a methane molecule. And the way I'm going to do this is by looking at the heats of formation of this overall reaction. So it's kind of like this one that we were looking at right here, but we aren't given this value. So we're going to calculate that value first, and then we're going to figure out what the average bond enthalpy of a methane molecule is. So let's go and do that. All right, so we're going to take methane in the gaseous form, and we're going to break it to give us carbon. And now this is gaseous carbon, and there should be one of them, and then 4 gaseous hydrogen monoatomic atoms. So this is how bond enthalpies are calculated. It's a little bit different. All right, so what would the delta H of this reaction be? That's our first question. Well, what we want to do is just make use of the enthalpies of formation that are given. So we'll take the enthalpy of formation of the products minus the enthalpy of formation of the reactants. And what we have here is carbon, 716.7, and then hydrogen, negative 74.6. Oh, sorry, 218. And then the reactant is negative 74.6. Okay, so if we want to break apart methane into its carbon atoms and hydrogen atoms, it's going to require a lot of energy, 1,663.3 kilojoules. Now, if we draw the methane molecule, we'll see that there are 4 bonds. So to break each of those bonds is we're going to require 1/4 of that energy. So there's 4 of them, right? So we get 415. And for this part right here, I think we can use to the 10th place. That's fine. 415.8 kilojoules per mole. And if we compare this to the table listed in 14.5, that's this table right here. It's 414. Okay. So that's actually really close. So this one is 414. Why is there a slight difference? Well, the slight difference is because this 414 is for other types of carbon hydrogen molecules. It's a complete averaging, right? So like ethane and propane, longer carbon chains as well. So the bond energy is going to vary, and so this is specific to this molecule. So that's just the way to say it. This is specific to methane, and this is an average of all CH bonds. Okay. Got a couple more examples. How about this one? Ammonia reacts with oxygen to form nitrogen dioxide and steam. And I want to know what the bond energy of the nitrogen-oxygen bond of NO2 is. Okay, so this is a little bit trickier. We're going to need to look up some of these values. Think about a way to solve this. Pause the video maybe, try it, see what you can come up with. The hint here is that you're going to need to know the change in the overall reaction. And the change in the overall reaction can always be determined through the enthalpies of formation of these individual things. And we can calculate that using the values that are in the tables. So that's where I'm going to start here. So I'm going to look up the heat of formation of methane, oxygen, nitrogen dioxide, and of gaseous water. So this one will be -80. This is going to be oxygen. Oxygen's always 0. NO2 is 34. And then water is, I want to make sure I use the right one. Come on. Okay, -242. Let's give me an issue again. Okay, come on. Great. Okay, so we'll figure out the enthalpy of the reaction by taking enthalpy of formation of the products minus the reactants. Could also use Hess's law if you wanted. This is essentially Hess's law, it's just using heats of formation. Okay, and then we have 4 moles of NO2. So I'm kind of just using shorthand here. So 4 moles times the enthalpy of formation of NO2 plus 6 moles times enthalpy of formation of water minus 4 moles times the enthalpy of formation of ammonia plus 7 moles times enthalpy of formation of oxygen, which is 0. That gives us negative 996 kilojoules per mole. Now we're not done yet because that just gives us the overall enthalpy of this reaction. And what we want to find is the bond energy of NO in NO2. Well, if we draw out each of these molecules, that's going to help us for the next part. So ammonia is NH3 like this. Now there are 4 of them, right? So if I wanted, I could draw 4 of these. I think that's going to be helpful for us to visualize what's going on here. Okay, and then we have oxygen, and oxygen is got a double bond. And there's 7 of those. Okay. And then on the right side, we have NO2. Now, NO2, let's see if we can draw this one correctly. Well, overall there are, let's see, 12 plus 5. Or 17 valence electrons. Now, because there's 17 valence electrons, this is going to have a radical, and we'll have a lone pair on the nitrogen. And we're going to need to have one double bond as well. The molecule is going to look like this with a resonance structure. So what I'm going to do is I'm going to draw the resonance hybrid here. And the nitrogen-oxygen bond for NO2 is actually of the bond order of 1.5. So it's like a mix of a single and a double bond. So overall we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 electrons that are drawn here. Now there are 4 of these that get formed. And then for the water, we're going to have 6 of those. Okay, so let's sum up how many bonds that are going to be broken and formed here. From the ammonia, we have a total of 4 times 3 or 12 NH bonds. And those are the bonds that need to be broken. And then we have 7 oxygen-oxygen double bonds that need to be broken. And then on the right side, we'll have 8 of these NO bonds, which I'm going to draw like this, where I have this kind of dash. That shows that it's a 1.5 order bond. So there's 8 of those that need to be formed. And as well, there's going to be 6 times 2 or 12 OH bonds. Okay, so that is quite a bit of bonds that are formed and broken here. So let's go and look at this table up here and find each of these values. So NH is 390. And overall, this is going to be equal to this value here that we calculated. Now, the bond enthalpy of oxygen is not 0. Don't get that confused with the enthalpy of formation. It's 502. And then on the right side, we don't know what this value is. So that's what we're going to be solving for here. So I'm going to set that equal to x. And then 12 OH bonds. Okay, so oxygen, hydrogen is 464. Okay, let's go ahead and start to simplify this. Okay, so this side here is 8,194 minus 8x, and then I can bring in this negative sign here. So negative 5,568. I'm going to bring the 8x over here, and then I'll bring the 996 over to the right side. Get 3,622. And that's the energy to form 8 of those NO bonds, and I just want one of them. So we'll divide through by 8 and get that it is 452.8. A lot of work. Kind of a cool thing that we can do. So that's the kilojoules per mole. This is essentially the heat of the enthalpy of a bond of the NO bond in nitrogen dioxide, which is a radical. What about if we compare this to the energy of an NO single bond and an NO double bond? Well, an NO single bond is not listed in this table. So if we go and look at this other table that this reference chart that we've been looking at here, if we scroll down to the end, I actually have some other average bond enthalpies that I have listed. I think I need to get rid of this little pin. Something's going on here. All right, I don't know why I can't select on this right now. But if we look at the NO bond, it's 201 for a single bond. And for N double bond O, it's the last one listed at 607. So 201 and 607, I'm going to write those down. And we can see here that if we average the two, that value is 404. So it's pretty close to giving us an average between the two. So what was that, 404? That's like an estimate. But for this specific reaction, with this specific molecule, since it's a radical, we don't know if it's a perfect 1.5 bond. There might be more single bond character in nitrogen dioxide, or actually in this case, it'd probably be more double bond character because this value is slightly more. But yeah, again, like this is why you would have to calculate that, because you can't, this value is quite a bit off. Okay, so that is that problem. I got two more difficult ones here to practice. Let's look at the enthalpy of this reaction where I have carbon in its solid form. This will be graphite. And I react it with carbon dioxide to give us carbon monoxide. And we know that the enthalpy of sublimation of graphite is 719 kilojoules per mole. What is the enthalpy of sublimation? Well, sublimation is a phase change I'll talk about in a little bit. When you go from a solid directly into a gas. So when carbon goes from a solid to a gas form, that is sublimation. And that's going to be equal to 719 kilojoules per mole. It should be a positive value because we're going to have to put in a lot of energy to get those molecules to be free from each other in the gas form. So the enthalpy of this reaction can be predicted, but what we need to know is I think what I was trying to do here is I was wanting to predict this by using bond enthalpies, and well, we can't do that when carbon is in the solid state. So we need to first convert it here into the gaseous state. Okay, so now we've done that. We know it's going to require this much energy. So if I want to calculate the enthalpy of this reaction, we'll need to add this energy in at the end. Okay, so let's look at CO2. And CO. So carbon monoxide is a triple bond. And it looks like this. And we have a positive and a negative and a positive side to it. And if we're going to form two carbon monoxide bonds, we'll need to break these CO double bonds. So let's find CO double bond up here. That's 730 a piece. And then the CO is 900 or so, 1,000. It's not given in that table, so I have to go back to this other one. Okay, CO is 1,072. It's on the right side there. Oh, actually it says here, specifically for CO and CO2, it's 799. So let's use that value. Okay. So we'll need to add that amount of energy to break those two bonds, and then this is the amount of energy that we get when we form a CO bond. And we'll form two of them. There's two of those. Okay. Wonderful. So a lot, subtract. Okay. 173 kilojoules per mole. That's the estimate that I'm getting for this. Okay. And that's estimating using bond enthalpies. And I think we could also do this using enthalpies of formation as well. And that doesn't take very long at all. Let's see what that comes out to be. I want to open this, I think, in this will be better. Okay, so if we look up carbon in a solid form, that's fine. What about CO2? That's negative 393.5. And then the other value was CO negative 110.5. Okay, so this is wow. Okay, I haven't practiced this yet, so like actually that is crazy that came out so close to that value. So here we have two different ways to solve the same problem, and they are identical. So nice. Okay, that makes me feel good about teaching you this. So I got one last problem here. It's to determine the enthalpy of combustion of propane using bond enthalpies. And then we're going to compare it to the combustion value I have in the reference table. Okay, so heats of formation, enthalpies of formation, the same thing. Okay, so first off, we're going to need to write the combustion reaction. So C3H8 plus oxygen. Oxygen is gas, obviously. We're going to have carbon dioxide, and we're going to get water, and we're going to use water vapor here. We have 3 CO2s. Oh, actually, if I'm going to use bond enthalpies, okay, I'm going to use bond enthalpies. I need to do this in the gas state. Okay, and then we're going to need to account for the difference here in the water. So, okay, we're going to need 4 water molecules, and then oxygen, there's 6 and 4, it's 10, so we'll need 5 oxygens. Okay. So the first thing that we're going to do is we're going to calculate this just using bond enthalpies. So C3H8 is going to have the structure like this, 3 carbons in a row, and then the carbons on the end will have 3 hydrogens each. And then the carbon in the middle will have 2 hydrogens. And then oxygen, we know the structure of. Carbon dioxide and water, we know the structure of. I like to draw just one of them when I'm doing this. We're not going to draw 5 of them again. It took way too long. Okay. So the enthalpy of this reaction is going to be estimated from the bond enthalpy of how many of these are there? There should be 8, I'm guessing. 3, 6, 7, 8. 8 CH bonds, which, if you remember from above, was 414 kilojoules per mole. And then for the oxygen, there are 5 of those. So I like to put a 5, a 3, and a 4 here so I remember how many of each of them there are. So there's going to be 5 OO bonds. Okay, I don't remember what that is. I'll look that up. It was 5O2. And then we're going to subtract these ones. And now there are 6 CO bonds here. And then there are 8 OH bonds here. Those are just single bonds. Okay, so CO, we said in carbon dioxide was 799. And then for OH bonds, we did that above 464. Cool. Let's see what we get. We get negative 2,684 kilojoules per mole of propane. Okay, so now this value is going to be a little bit different than the combustion value listed up above, because we're not accounting for the fact that the combustion value above has the water going from the gaseous state to the liquid state. Okay, so when water goes from gaseous to liquid, that's going to be known as the condensation of the gas. So it's going to condense down to being a liquid. So what is that delta H value going to be? Well, we can calculate that. We're going to take the enthalpy of formation of the liquid and the gas. So we'll just subtract the two. So when we condense this liquid, it should give off energy. So it's going to be negative 286 minus negative 242. I don't know why it's doing this to me today. Oh my god. Never mind. I'm just gonna keep it on my other screen here. So I'm subtracting the formation of this minus the formation of that. Okay. So it gives off negative 44 kilojoules for every mole of water that condenses. So this value here, we're going to need to add an additional 4 water molecules, so 4 times this value. Oh, no. Okay, negative 2,860 kilojoules per mole for the combustion of propane. Okay, so I said compare it to the value listed in the reference. So let's find that reference value. Combustion. Where's the combustion table? Here's the combustion table. Propane starts with a P. C3H8. 2,220. Huh. Well, this is an estimate using bond enthalpies, so it could be off. Additionally, and again, this will be a negative value from that reference. I need to look back at my work on this one and see what I did wrong. If I did something wrong. Oh, I know what I forgot. I forgot the carbon-carbon bonds. So there are also these bonds here that I didn't account for. Okay, so there's two of them, two carbon-carbon bonds. Okay, so let's see what that bond energy is going to be. That's going to be 347. And okay, so that's going to be on top of, I think I can just add it into here. It's easier for me to do it this way. I don't know why in my head. 2 times 347. Okay. This value. Okay. And now, are we closer? We're definitely closer. Ooh, I like that better. That looks a lot nicer. Negative 2,166. And that's pretty close. So what is this percent error here? Yeah, 1.5% error. Okay, so yeah, it's sometimes tricky to do these problems. You know, you forget things like this, and you'll be like, oh yeah, I mean, it's off by a lot, but no, really, like you just need to. I just need to practice more. These problems are really rough. Okay, so where are we at right now in our time? I think we are at an hour and 20 minutes. So I'm going to try to go through some of this other stuff fairly quickly. Calorimetry is, I think, an easy concept to understand. This is, I think, the hardest part about chemistry. It's just all this thermochemistry. So calorimetry, this is the measurement of heat that's transferred due to the difference in temperature between two objects. So if you take hot water and you mix it with cold water, you'll reach an equilibrium temperature, and the hot water is going to be transferring its heat to the colder water. And a substance's resistance to temperature changes is known as its heat capacity. The heat capacity is simply the energy divided by the change in temperature, or the heat energy divided by the change in temperature. But we'll typically do it per gram or per mole of a substance. So when specific heat has the units of joules per gram degree C, it's going to be referred to as the specific heat. And it's going to have the symbol of lowercase c, and oftentimes with Hold on a second. Oh, why is this on? There's another laptop in the room, and it was just like heating up like crazy. I don't know why it was on. So it's generally given a lowercase c and then the symbol P here for that. This is going to be measured at constant pressure. And then when heat capacity has the units of joules per mole degree Celsius, it's referred to as the molar heat capacity. That's given a capital C, and when measured at constant pressure, it's given the value Cp, lower capital C. Now you can also measure heat transfer at constant volume. I'm not going to be really talking about that too much. So let's look at 3 different objects. I have copper, I have aluminum, and I have water. And when we look at this table here to the right, we see that copper has the highest specific heat capacity of the 3. Or sorry, the lowest, 0.385. Aluminum is 0.87. And then water is 4.18. And what this is referring to is the amount of energy that's required to increase 1 gram of a substance 1 degree Celsius. What this basically means is a substance that has a low value is easily heated, and a substance that has a high value takes more energy to heat. So it's going to warm up slower, but it actually cools down more slowly. So water here actually is a large chain. It has a large storage of heat when it's hot, because it takes a long time for it to cool down. And I'll talk about at the very end where this energy is stored in the molecules. So I think that part's the most interesting to me. When we look at different substances, like we'll see a range of specific heat values. One thing that's interesting is if we look at the molar heat capacities, we see that the things like paraffin wax have an insanely high value for this. So if you're going to be low on energy, you want to store some wax candles around and burn those, because there's just per mole, there's just a ton of energy stored in those carbon and carbon hydrogen bonds. But some of these values we'll notice are like all the same. And I'm just going to point those out here in yellow. And we'll come back to this later. Why are all these the same value? These are monoatomic gases, argon, helium, and neon. So why are those all the same? Okay, we'll come back to that in a little bit. So a calorimeter is how we measure the heat of a chemical reaction. It's also how we can measure a physical change or the heat capacity of an object. So a constant pressure calorimeter measures change of heat that occurs in solution. So I talked about this a little bit in the last lesson. You have an insulated container, and inside is a solution of water, and then you have your reaction mixture that you put in there. The reaction's either going to require heat from the surroundings or give heat to the surroundings, and you'll measure a change in the temperature. That heat transfer at constant pressure is known as the enthalpy change. If you want to do this at constant volume, you'd use a bomb calorimeter, which resists a change in volume, and you're just measuring the internal energy change of the system because there is no volume change. The difference between delta U and delta H is very small. There's some sections in your textbook that talk about it. It's about 1% difference. For me, not being a physical chemist, that nuance difference isn't super important to me, but it is to other people. So if you go on to take physical chemistry, you may learn about that difference. And then when we want to look at the specific heat capacity of a substance, we can just look at how a hot object transfers heat to a cooler solvent, and that difference in temperature can be used to help you measure the heat capacity of that substance. So let's look at the latter case. If I have a beaker of water containing 50 grams of water and a separate container that contains 50 grams of acetone, and they're both originally at the same temperature, and then I mix the two, the first question I ask is, which of the two liquids is going to have a higher final temperature? Well, the water here has a larger heat capacity. Sorry, I'm totally reading this question wrong. If both beakers are heated with the same amount of energy, which liquid will have the higher final temperature? Well, the water is going to heat up more slowly, so the acetone, for the same amount of energy, will have the higher final energy. So the acetone takes less energy per gram, so it will have the higher final temperature of the two. Okay. Now, if we want to figure something out that's a little bit more complicated, we're going to need to know a equation, and the heat transfer equation is Q equals the mass of an object times its specific heat capacity times its change in temperature, or the heat is equal to the moles of that object times its molar heat capacity times the change in temperature. Now, how much energy is released when 20 grams of water is cooled from 50 degrees Celsius to 30 degrees Celsius? The specific heat of water is 4.18 joules per gram degree Celsius. Okay, so when we cool water, or when water is cooled, it releases its heat to the atmosphere. So that's going to be a negative Q value. The mass of the water is 20 grams. The specific heat is 4.18. And the change in temperature is negative 20 degrees. You can use these in Kelvin or Celsius. The change in 1 degree Celsius and 1 degree Kelvin are the same. Negative 1,672 joules. 3-sig-figs, 2-sig-figs, whatever you want to use. All right, so next one, when a 50-gram block of copper is heated with a certain amount of energy and its temperature increases, what is the specific heat of the copper? Okay, so we're going to use the same equation. Q equals mc delta T. And we don't know what C is, so we'll rearrange the equation for that and find that Q is Q divided by the mass times its change in temperature gives us the specific heat. Q over the change in temperature is just heat capacity in general, by the way. So we have a positive 1,046 joules, 50 grams, and the temperature change here is 54.3 degrees. And we get the same value that was listed above, 0.383 joules per gram degree C. And when you do these experiments, oftentimes your change in temperature is going to be different than what you'd theoretically expect. It has to do with the fact that a lot of the heat that's released during a calorimetry experiment goes to heating up the calorimeter. So unless you're calculating the calorimeter constant, your specific heat values will be slightly off. I'm not going to go into that. You can, if you want, you can read about it in the textbook. I'm not going to ask any questions on calorimeter heat capacities. What's the final temperature when a 90-gram sample of aluminum at 20 degrees Celsius releases 500 joules of energy? Okay, so here we're rearranging this equation to solve for temperature. So the change in temperature is going to be equal to Q over MC. It's releasing 500 joules of energy, so that's negative value. We have 90 grams, and the change in specific heat capacity is 0.897. Okay, so the final temperature is going to decrease by 6.19 degrees Celsius, so 20 plus that value. So the final temperature is going to be equal to 13.8 degrees Celsius. Another way you could solve that is saying, delta T is equal to T final minus T initial. So T final minus T initial will, T initial is just 20 degrees Celsius. That equals negative 6.19. That's another way to get that. All right, so this other one here, this is more or less what you'll see on certain problems. If I have a solid sample of gold and it's initially heated to 69.3 degrees Celsius, I then drop it into a known mass of water at a specific at a temperature that's lower. The gold is going to transfer its heat to the water, and the water will increase in its temperature. The final temperature of both substances will be the same, and we can calculate the final temperature by looking at the loss in energy from the gold and the gain in energy from the water. So the heat that's transferred from the gold is going to be equal to its mass times its specific heat value times its change in temperature. So T final minus the temperature initial is the hot temperature. And then the heat that's absorbed by the water is going to be equal to the mass of that water times its specific heat times T final, which is going to be the same as the other T final, minus the temperature that it is at the cold temperature. Okay, so that's now one thing that to keep in mind is that the Q of the gold is going to be equal to the negative Q of the water. So the energy that is released by the gold is going to be equal to and opposite the energy that's gained by the water. Another way of putting this is that the sum of these two has to be equal to 0. Okay, so we'll make use of this relationship. Okay, so if we combine all three of these things together, what we will get is something that looks like this. So I'll set this equal to and opposite this. And I'm going to replace in these values. So this one was 69.3 degrees, and this one was 27.8 degrees. And at this point, I just usually distribute everything and then recombine it. You can be a little different. You can do it a little bit differently than that, but that's generally how I do it. It's easier. So this number, 4.0119 times TF, and then I had to take that same number and multiply it by negative 69.3. And on the other side, take negative 64.2 times 4.18. And that'll give us negative 268. I don't want to use that many sig figs. It's just too many. TF. And then we'll take that same number, multiply it by, what is it? Negative 27.8. Positive 7,460. Okay. What I usually do is I'll move the TFs to the same side so that they're all positive. So this number, positive plus 4. Okay, so we have 272.4 TF equals, and then I'll move this other value to the other side. And we know that the final temperature has to be between the two. And we know that the final temperature is probably going to be closer to the initial temperature of the water. And that's because the water is going to resist the change in temperature more than the gold is. And we find that the TF is 28.4 degrees Celsius, which is indeed very close to that initial temperature, but it's more. So the specific heat capacity of water is way higher than the specific heat capacity of gold. It's 32 times as much. So for any, so the water is going to change 32 times less than the gold is. So there's probably some other hacks for solving these problems, but that's generally how I work through those. And as long as you don't make any sign errors or any algebra errors, you'll usually get it. Okay, so let's talk about phase transitions, and I'll close off with some molecular basis of heat capacities. Sorry, this is so long. Energy is transferred when a substance changes states. We're kind of familiar with this already. Down here I have a solid, I have a liquid, and I have a gas. So what's occurring here just one second. we need to input energy anytime that we want to change a state to be more disorganized. So in a solid in the solid state, there's a lot of attractions between the particles there. So when we input energy, we end up weakening the attractions that are between the particles. So these can be covalent bonds, or they could be, in this case, we're looking at phase changes. So we're not actually breaking any bonds. We're just breaking intermolecular attractions, which would be those intermolecular forces we talked about, dipole-dipole, dispersion forces, and hydrogen bonds. If we take a substance and it goes to a liquid or a gaseous state, this is when we have energy that's released. And we strengthen the attractions in the process. All of these values that go up, these have delta H values that are going to be positive. They'll be greater than 0. And then all of these ones are going to be delta H values that are less than 0. Let's take a second and define all of these terms. A solid going to a liquid is the melting process. A liquid going to a solid is the freezing. A liquid that goes to a gas, that's known as vaporization. Gas to a liquid is condensation. A solid to a gas, I talked about that above, that's sublimation. And then the opposite process is deposition. And these can occur at low pressure conditions. You can go directly from a solid to a gas. There are some also substances that do it at room temperature. Okay, so if I have ice, which is a solid form of water, before the reaction occurs, we're going to have a bunch of water molecules that have hydrogen bonds to each other that we're going to kind of break. I'm going to draw like this. Actually, I'm just going to draw it a little differently. Draw it simply like this. And then during the reaction, what we're going to need to do is we're going to have to input a bunch of energy, right? So we input energy into the system to break these attractions. So we break the hydrogen bonds, and instead of having 4 hydrogen bonds, they have like 2 to 3 now, so they can flow over each other a lot easier. So this process is always going to be endothermic. You need to add in a lot of energy to the system. When you freeze water, it's the opposite process. So you start off with something that's kind of disorganized, and you make it more structured. We're going to form more hydrogen bonds. We have to take energy out of the system. This is the weird thing. In order to do that, this is exothermic. This can be hard for me to wrap my brain around, because I'm like, wait, if we want to make it more structured, shouldn't that require energy? But it's actually opposite. It takes this state here is more stable. So when you have a stable state, it actually releases energy. Okay, the heat transfer during the phase transition. Well, there is no temperature change during a phase change, but there's still heat that's being transferred. This is known as the latent heat. So during the melting process, energy is needed to change a substance from a solid to a liquid. And at constant pressure, this is known as the enthalpy of fusion. And this is not to be confused with the fusion that occurs in a nuclear reaction. What did I just do that? And then the opposite process is known as freezing, and the energy change is equivalent to the negative of the enthalpy of fusion. So you can, if you know the enthalpy of fusion, you know that the enthalpy of freezing is the same value, but just opposite in sign. Same thing for enthalpy of vaporization. This is vaporization is a liquid to a gas. That has a certain value you can look up. The opposite process is enthalpy of condensation, and equal and opposite to the enthalpy of vaporization. Okay. And you can also have the enthalpy of sublimation and deposition. These are latent heat processes, meaning there's no change in temperature. They occur at constant temperature. Here are some molar heat of fusion and vaporization values for some common substances and their melting points and boiling points. With this data, you can figure out a heating curve really quickly. We'll see that the heat of fusion of water is quite high compared to some of these other substances, which are, got less intermolecular forces. So water has really strong intermolecular forces. Interestingly, carbon dioxide has a high heat of fusion, as well as ammonia makes sense to me. Okay, so let's look at how much energy is required to melt a substance. So when we melt something, that's going to occur at a specific temperature. It occurs at the melting point. I think this is wrong. Lead does not have a... this could not occur, so this is wrong here. If we're melting lead, that means it occurs at its melting point. This would be at 327.5. So here we're going to use the molar heat of fusions. In order for us to do that, we need to take the mass and convert it into moles. So we know how to do that now. Lead is Pb. We'll have to divide it by the the molar mass of lead. I'm looking that up. 207.2. Okay. And then what we're going to do is we're going to multiply this by the heat of fusion. Okay, so the heat of fusion is 4.8 kilojoules per mole. So our energy here is going to be equal to 0.463 kilojoules per mole. Now, 20 grams of lead is like 1/10 of a mole. So that is essentially 1/10 of the heat of fusion. That makes sense. Okay, so how much heat is released by the condensation of 2.88 moles of oxygen at negative 183 degrees Celsius. So here, I think I have the right value, negative 183. Yes, I do. This is because condensation is the opposite of vaporization. So that would occur at the boiling point. And oxygen has a very low boiling point, as oxygen is typically a gas at room temperature. So we need to cool it down quite a bit. But once we get it to that temperature, it will transition from a gas to a liquid, and it's going to be equal to the negative of the heat of vaporization. So that's 6.82 kilojoules per mole. Giving us negative 19.6 kilojoules. Oh, it's not kilojoules per mole, it's just kilojoules. There we go. A lot of energy that would be released in that case. So when studying the energy required for the transition between phases, we often will plot temperature versus energy diagrams. When energy is absorbed by the system, this is known as a heating curve. And when it's released by the system, it's known as a cooling curve. So what we can do is just do this for one problem, and I think you'll get the idea of it. If I want to take ice at negative 10 degrees Celsius and heat it to steam at 130 degrees Celsius, I'm going to need to heat it until it gets to its freezing point. That'll be the first step. Then we're going to need to melt the ice, and that'll be at a constant temperature. At that point, then, we're going to need to increase the temperature to 100 degrees Celsius. So that's going to take some more heating that occurs. And then we'll need to vaporize that liquid. And the vaporization is going to take up actually the most energy here. That's going to be the most heat here. And then we'll need to heat it further until it's at 130 degrees Celsius. So there's 5 different steps that we're going to be looking at. 1, 2, 3, 4, and 5. The odd steps 1, 3, and 5 are all just the application of Q equals MC delta T, and 2 and 4 are just making use of the heat of fusion and the heat of vaporization. Okay, so step 1, heat ice to the boiling point. So Q equals MC delta T. Now, the specific heat of ice is different than that of water. And I don't know if I have that listed here. So let me show you. There's another handout I have this week. It has all this values listed on it. Let's take a look. Right now it's called midterm 4 equation sheet. I guess I'm going to call it final equation sheet. But we can see here that the specific heat of ice is 2.10. Let's grab actually these values here. What is going on? It won't let me paste it. There we go. Okay, so we're going to use these values here. It actually takes less energy to heat ice than it does water. So this will be 20 grams times 2.10 times the change in temperature here. So the change in temperature is going to be 0 degrees minus negative 10, or a change of 10 degrees Celsius. So I'm going to kind of work through these as we go through them. That's going to be 420 joules of energy. Second process is we're going to heat, so we're going to melt ice. at the boiling point. So when it's at the boiling point, there is no change in temperature. So we'll use the equation Q equals N times the heat of fusion. So we'll need to divide by the molar mass of water. I'll use 0.2 for this. And multiply by the heat of fusion, which is 6.01 kilojoules per mole. Okay, so now this is in kilojoules. So what I'm going to do is I'm going to convert this one to kilojoules as well. Okay. Next part is to heat water to the melting. Oh, wow. These are melting points. Heat water to the boiling point. You're probably thinking, what is he doing here? Q equal. So we're going to use the same thing here. So we use Q equals MCT. And this is a different value. As we can see here, it's 4.18. And the change in temperature is 100 minus 0. And that's going to be 8.36 kilojoules. I'm going to convert that right away. Next thing is to vaporize the water. Okay, so we'll use Q equals N delta T. What's 20 divided by 18? Not multiplied by, but divided by. This value is much higher. It's 40.68 kilojoules per mole. So the energy that's required to vaporize any substance is always much higher. (45.1 kilojoules. And the last thing is to heat the steam. And specific heat of steam is close to that of ice. It's 2.08. And we're going from 130 as our final, starting at 100, because we're starting at the boiling point. And what do we get? Doesn't take much energy here, 1.248 kilojoules. And then what we do is we're going to add all these values up. I did it wrong because I didn't. What? I'm just going to restart over. I don't know what I did. Good. 61.7 or 61.8 kilojoules of energy. It takes a lot of energy to heat up water that much. And there you have it. So that's how you do heating curves. It's how you make use of heat capacities and enthalpies of phase changes. to figure out the heat of a certain process. This is just physical changes, not a chemical reaction. Okay, so the last part of the lesson is something I'm going to keep fairly short. It's just the idea that the heat capacity of a substance is dependent upon um, uh, some physical properties of that substance. And when we're looking at an when we're looking at a how a molecule behaves, it's not a static molecule. It's actually constantly in motion. Um, and this video here is really good. So if we have thermal energy and it's being applied to a system of a bunch of different gases, what we can see is that those gases are going to be moving around in 3 dimensions. That's called translational motion. They'll be rotating around. And then additionally, um, the atoms themselves will be vibrating to some extent. And I don't think you can really see the vibrations occurring here. We can mostly see the translational and the rotational motion. And the the temperature is dependent upon just the motion, but the energy can be stored in the motion as well as the rotation of those objects. So this video talks about that in more detail. Um, so it talks about the different, degrees of freedom that an object will have. And every particle is going to have 3 degrees of translational modes of freedom. So they can move in the x, the y, and the z direction. But a binary molecule, something that's linear, can rotate in 2 degrees. It can rotate this way, or it can rotate this way. We don't worry about this rotation, so we're not counting the rotation like this. This one doesn't count. So for a linear molecule, you'll have 2 degrees of rotational freedom. And then right now we're ignoring the vibrations, but let's see, for a linear molecule here. Let's see if I can find one. I don't think it talks about it in context with the other one. But for nonlinear molecules, there's an additional degree of rotational degrees of freedom, and that's all summarized kind of in this context. And if you're interested, you can read about it. It's also at the end of your textbook. But for the translational degrees of freedom, we have x, y, and z coordinates, and we can define heat capacity as the change in heat per change in temperature, or the enthalpy in change in temperature. And we'll find that for a monoatomic gas, that the specific heat value comes out to be 5/2 R. And the gas constant R, when written in joules per mole Kelvin, is 8.314. So you can actually calculate that the specific heat of every monoatomic gas has a value of 20.78 joules per mole Kelvin. And that's the same energy, or same values that are in this table up here, 20.78. All the other values are going to be greater than that, and that's because those molecules can store energy in terms of rotations and in terms of vibrations. For linear molecules, you can add another R value, giving us 7/2 R, and for nonlinear molecules, it comes out to 8/2 R. And then lastly, if we have vibrations that are occurring, we can determine how many degrees of motion there are for that by counting the number of atoms and multiplying by the 3 coordinates and then subtracting the rotational degrees of freedom. And you can find the how many vibrational modes there should be for that molecule. But yeah, so let's look at this graph here. This is like the last one. And we can see that we have the noble gases down here. They have a heat capacity that's 5/2 R all the time. It doesn't matter what the temperature is. But for a molecule that's linear and like hydrogen and nitrogen and oxygen, there's additionally this vibrational component, this rotational component that causes these CP values to get a lot higher. And then the specific heat capacity values can get even greater for these molecules that have vibrational components as well added in. And for these are like your nonlinear molecules, water and carbon, carbon dioxide's linear, but water is nonlinear, and so it starts off at a value that's 8 halves R. So here's nonlinear, linear, and monoatomic. And we got translational, rotational, and vibrational components that add in and cause these molecules to absorb more heat or less heat, depending on each of those degrees of freedom. So when you go on to study more chemistry, you can study the vibrational modes, and that can actually help you distinguish different molecules using spectroscopy. And it's a really interesting thing that we can do. All right, so that's the last thing in today's lesson. And hope you enjoyed the course. If you have any questions about today's lecture, feel free to reach out. This is probably the hardest topic in general chemistry is thermochemistry. And hopefully these work through examples helped you master some of that. So take care and talk to you soon.